of answers. Or wrong question. Yeah, this was a mixed up problem here. As this was supposed to be a true or false. As the temperature increases, so does its kinetic energy. True or false? True. These are the wrong set of answers. So something like this is definitely something wrong with this problem.
So I spent like 2 hours last night going through that. I was like, I have no idea how the hell that's supposed to be answered.
All right, sorry about that, you guys. It's impossible. So this is kinetic energy. So you're looking for a percentage for the kinetic energy? Yeah.
I was like, maybe?
Yeah, that could be, but it's wrong. Some of the other problems too are, this was over the summer, so they have less time for memorization. So I started, I jumped ahead and started some memorization stuff early. And so, let's see.
Space FD. Oh my god. Okay.
Yeah, so some of these, like chloride ions.
That's Cl plus or Cl minus, right?
Cl minus, yeah, or Cl plus. It would be an ion. But usually you can tell because of the ending. If the ending is like with an IDE, it's always a negative charge. Now, if it was like chlorine ion, then you can't tell. It would be positive or negative.
And that's beryllium solid, correct?
That's beryllium solid, right?
And then
S2 minus. S2 minus we're going to try.
Isn't it?
It's a sulfur ion, but since it's negative charge, we can call it sulfide ion, yeah. But that's chapter 6, by the way. So,
because like the end of chapter 5, there's like half, it's not like Peter on a table.
Yeah.
You want us to memorize that?
No.
Okay, cool.
47, that's chapter 6 also. So some of this is different. You aren't going to expect this on your test. All right, any other questions on this?
So that's how the format's going to be kind of...
The format's going to be exactly the same as this, pretty much.
90% true or false, not true or false.
Multiple choice, yeah.
4 or 5, short answer.
Yeah, except the points of the multiple choice aren't worth that many points. So, whereas the short answer ones are probably. I have to look at the exam tool because your exam is out of 100 points. I can't remember over the summer if I made this. This might be more than 100 points, but I'll have to take a look. For the most part, your test will be very similar to this test. 2 pages long. Probably the first part of the lab will work on the calculations for the report, and then the second part will take the test. We'll give you about 2 hours.
Wait, can you repeat that?
The first part of lab on Thursday, we don't have any formal lab on Thursday, but we'll work on our lab report from the past experiment. And then on the second part of the lab, we'll do the exam. So you'll have at least 2 hours for the exam. 2 hours for the exam, which should be plenty of time to go back through. It's only 2 pages, so an hour per page. Or, it's less. Depends on how you do it. No more. All right, any other questions? Okay, so we did some practice here with the nuclear symbol. The nuclear symbol tells us about composition. So what can we do? What we try to do is we try to correlate, little observations with something in structure or composition. And so when we're thinking about this, let's take one of the earlier things we looked at, and that was the size. So we know hydrogen's bigger than helium. And so we'll try to correlate some of its composition or structure with this. So we know what the structure is. What is the structure? Well, the structure is the nuclear atom model. The composition is the, well, what are atoms made up of? Protons, neutrons, and electrons. And so we take a look at how the protons, neutrons, and electrons are arranged. And so, for example, in the hydrogen, when you look at hydrogen 1 has how many protons? One proton. That's in the nucleus. The nucleus is very tiny. This is actually, if this were the nucleus, let's say this is actually more than, this is about 2 centimeters, maybe 2.5 centimeters. You know, if the nucleus is 2.5 centimeters, how big is the atom? The atom is going to be about, it would be about 2.5 football fields. And so this is, the size of the nucleus is over-exaggerated here. It shows you how much of the atom is empty space. You know, the nucleus would just be a tiny dot here. Right? But that's where all the mass is. This is what gives the nuclei horrendous densities. The density of a nucleus is on the order of tons per cubic centimeter. You know, and that compared to gold or even iridium. Iridium is one of the most dense, if not the most dense. Iridium and osmium, two most dense elements on the periodic table. And when we compare it to those, it's nothing. And so, anyway, we have a proton. What's the charge on the proton? Positive. For hydrogen 1, are there any neutrons in the nucleus? No. And then the atom consists mostly of what? Empty space, and the electron is kind of free to roam. The electron has a negative charge. So the P, I'm going to write P plus, E, I'm going to write E minus here. And so this is it, the hydrogen atom. And when we're talking about the diameter, there's no fixed wall. You know, is there a fence here that fences in the electron? Actually not. You know, the electron can.
Wouldn't the electron shell be kind of?
Electron shell is the thing for statistics. That is, you know, what is the probability of finding the electron outside the shell versus inside the shell? The shell is an imaginary boundary itself, and it's like this. Inside the shell is like a 90 or 95%, depends on how you draw the shell. Probability of finding an electron in there, and then a 5 or 10% probability of finding it outside the shell. And so it's an artificial boundary so that we can mark the probability. But anyway, the electron is confined to the proton here. If the electron escapes from the proton, you know, we call an ion. How can the electrons escape? Well, something can forcibly knock it off, you know, create that, or something can come along and steal the electron. But anyway, what holds the electron to the proton, or what prevents the electron from escaping? What prevents the electron from escaping are Coulombic attractions. And what do Coulombic attractions depend on? The charge. And so the higher the charge, the what do we say? The stronger the attraction. The lower the charge, the weaker attraction. And so the charge here is +1 for the proton, -1 for the electron. And so this is attraction. Opposite charges attract. Now, well, that's going to keep the electron there. So this is why measuring radii is difficult. Measuring radii or diameters of atoms is difficult because there is no hard shell. There's no firm boundary. You know, the electron is free to roam in this area, so it depends on how much resistance you have coming in here. All right, this is the hydrogen. Now, let's go on to helium. Let's take a look at helium-4 by far the most stable. Helium-4 consists of what? Four protons? It's 2 protons, yeah. It's going to be 2 protons. This would be the mass number. I didn't write 2 here because helium is element number 2. And so we should know that there are going to be 2 protons. And remember, the protons seems to dictate the properties, right? And so the 2 protons here, are there any neutrons?
Yeah.
Yeah. There's going to be 2 neutrons in there. And they're arranged some way. You know, there's that picture, cartoon sketch that, you know, is that really how the protons and neutrons are arranged? And so what nuclear chemists and particle physicists are very interested in is in the structure of the nucleus itself. You know, how are the protons arranged there? Are the protons like spherical? You know, atoms are spherical, and people have detected that. Are protons spherical? Are neutrons spherical? You know, what exactly do they? How can you visualize them? And so that's the realm of the nuclear physicist. So I talked about, you know, the size of the nucleus. The size of the nucleus, though, can be measured. It's something that can be measured.
Picometers, right?
Well, the size of the atom is on the order of hundreds of picometers, and so the nucleus would be like 2,000 times smaller, so it'd be like point something picometers, you know, on that order. But how big is a proton itself? How big is a neutron itself? You know, that's a realm of particle physics. How big is an electron? Well, we know how much an electron weighs, but how big is it? You know, if this is mostly empty space, then the electron must be tiny, right? But if you get into physics, the physics of this, the electron is a very bizarre thing. Because if you ask like a particle physicist, nuclear chemist, how big an electron is, you know what they'd say?
It's large.
They'd say it has zero size. Electron has zero size. Anyway, we'll talk more about the electron itself, but you know, we aren't going to concern ourselves with the size of the electron, other than it's got to be small. You know? Now, how many electrons do we have here? We have 2 protons, 2 neutrons, and 2 electrons. The electrons keep or maintain the balance. Now, are the 2 electrons going to be paired up? Are they going to be together? No, the electrons, you know, electrons don't like each other. Why? They both have negative charge, so they kind of stay away from each other, or try to. Sometimes their paths come together. But this is one of the relations. Well, like, what's one of the differences? Well, one of the differences is you look. I mean, the electron has negative charge, but when you look at the nucleus, this nucleus compared to that nucleus, this nucleus has a much higher positive charge. In fact, twice the charge. If this nucleus has twice the charge, then Coulomb's law says that it should have 2 times the attraction, 4 times the attraction. What would Coulomb's law say? It would have twice the attraction. And so if this has twice the attraction, it's like it's going to pull the electron much closer. Light opposites attract. And so one of the things right out I've noticed is that this electron is going to be pulled closer. And this electron would see the same nucleus here. This nucleus is 2 plus, even though there's an electron on the other side here. You know? And this electron is going to be pulled closer. And so if the electrons are pulled closer, then this imaginary boundary that we have is a lot smaller, right? Or the radius, or the diameter is going to be smaller, you know, because as we come in closer, we aren't going to hit that as much as over there. Does that make sense? And so this is the type of stuff we look for. We try to correlate composition structure with properties. So we know some properties. Let's try to figure out, is there some kind of thing we can correlate with those properties? And so one of the properties is size, right? And so and so does this make sense? Okay, then let's make a prediction about lithium. If we make a prediction about lithium has how many protons?
3.
Lithium has 3 protons. And, actually, let's look at lithium. What's more common? What do you think is more common? Lithium-6 or lithium-7? It turns out that, there's 2, and lithium-7 turns out to be the more common one, just based on observations in nature. And so, if it's lithium-7, it has 3 protons and how many neutrons? 4 neutrons in the nucleus. So if it has 3 protons, then it's got to have 3 electrons. Each of those electrons kind of try to stay away from the other, right? And so if the electrons are trying to stay away from the others, then it'll be spread out in this empty space. But now, think about Coulomb's law. We have
plus 3. Plus 3 will be 3 times stronger than plus 1, according to Coulomb's law. And so this is going to pull in the electrons even closer. But is lithium a smaller atom than helium? No. Is lithium a smaller atom than hydrogen? No, lithium's bigger. Lithium's bigger than both. And so, we tried to do this. We tried to find a pattern. We tried to correlate it with something in terms of composition and structure, but unfortunately that failed, right? For right now, it failed. And so there must be something else there. But what else is there? I mean, we just have the nuclear atom model. In the center, there's a nucleus. Surrounding the nucleus with electrons. We had, what was that experiment that determined the nuclear atom model? Rutherford's? Yeah, Rutherford's, what was it? Rutherford's CRT? No, Rutherford's gold foil. The J.J. Thomson CRT was used for the electrons. So we have, we have this, so what's wrong? Are we missing something in the composition? No, we aren't missing anything in the composition. The atoms consist of protons, neutrons, and electrons. Is it the nuclear atom model? Yes, it is, because of the Rutherford, they provide pretty solid evidence. So what else is there? Okay, what else is there is, like I said, the electrons are kind of bizarre things, right? The electrons aren't like your normal little spherical particle. And electrons, there's something about the electrons here. It's like I said, the nucleus is the realm of the nuclear physicists or the nuclear chemists. And so it turns out that there is something more to this structure. And so this is why we call it atomic structure part 1, because it turns out the electrons are organized in a much more complex way than I show here. If it were just simply surrounding it, then lithium for sure should be smaller. So there's something more to it. And so it doesn't make sense. And it doesn't make sense. Well, everything we've said is correct. The higher the positive charge, the stronger the pull on the electron is, the smaller the size. That's true. And so this is not an exception to Coulomb's law. And so what we need to do is we need to do some more, what? Can you come up with a hypothesis right now? I don't think so. I mean, maybe. What we need to do are more observations. So let's go ahead and take some more observations and stuff. Well, anyway, some of these observations have disproved features of Dalton's theory. Indivisible nature of atoms. Atoms have subatomic particles that they can be broken up into. And then the problem with the isotopes. All atoms of an element are identical. It's not true. All atoms of an element have the same number of protons. Since that's fixed, that's what we call the atomic number, or the element number. All right, the masses should be simple, right? We know what a proton weighs about. How much does it weigh about? 1 U. And the neutron weighs about 1 U, and the electron weighs about 0.05 U. And so we could come up with some ballpark estimates for the mass of the atom, right? Ballpark estimates, which we will. So we have the atomic mass unit. It's more properly defined as 1/12 the mass of an atom of carbon-12. can you divide or can you break up the carbon into 12 pieces, the carbon atom into 12 pieces? No, that doesn't work. There's something wrong with this slide as well. It's supposed to be 1 U is equal to 1/12, the mass of one carbon-12 atom. Atomic mass? Okay, now this. You know, we're dealing with lots of atoms. So for example, in about 12 grams of carbon, we have 602. 602. Let's see how many. And so there are two types of chemistry. Okay, you have the chemists that are working with single atoms and single molecules. You know, like the mass spectroscopists are working with single atoms. You know, they shoot single atoms through their machine. You have other physicists who are working, and chemists who are working on chemical reactions, you know, at the atom level. And so you have you have people working on particles. And so we're looking at individual particles. So, for example, if I look at a graphite sample in nature, and there are going to be a whole bunch of atoms in the graphite. I'm just showing how they're linked together. The atoms actually are touching each other, but sometimes we spread out the atoms so that you can see the geometry of graphite. Graphite likes to form these hexagonal rings. So if we're looking at individual atoms here, then we need to know, you know, because there are two types of carbon atoms. What are they? The two types of carbon atoms are C12 and C13, carbon 12 and carbon 13. We'd like to know that because carbon 13 weighs a little bit more, 1 U more, roughly, than C12. And so here, you know, is this a C12 or C13? Makes a difference. If most of these are C12s, once in a while we'll hit a C13. And so let's make the white one C12. And so we go through, let's say, 10,000 C12 atoms like this, and then hit a C13. You know, like a black one, C13. So C13 is rare, but still, we have to account for that. There's C13 present in here. So we'll make the black one a C13. And so if you're taking some kind of laser or something and vaporizing atoms off the surface, then you'd want to know, did you vaporize a C12 or a C13? However, you know, there are chemists that don't work with individual particles like this. There are chemists that work with macroscopic quantities. If you're dealing with macroscopic quantities, let's take 12.01 grams. You know, 12.01 grams you can see easily with the naked eye. So if we go with 12.01 grams of carbon, you know, how many atoms are there? Well, this is a calculation we're going to do pretty soon. Not yet, but you know, it turns out that this number, there are 6. Okay, so we're going to have, this is going to be 1,000, 1,000,000, a billion, a trillion. What comes after a trillion? Let's see, did I get this right? 22. I didn't get it right. Shoot. All right, how many zeros do I have? I have 6022. So 1, 2, 3. I have 20 zeros here. So this is going to be 1,000, million, billion, trillion. Actually, that's as far as I can go. Trillion. So 1,000, million, billion, trillion. So up to here, it's a trillion.
Isn't it quadrillion, quintillion?
Yeah, it'd be that. I'm not going to use that actually because I'm going to do it differently. I'll just add on to it. 1,000, a million, a billion. So this would be a billion. This would be a billion trillion. So this is going to be 602.2 billion trillion atoms. So if I have 12.01 grams, I have 602.2 billion trillion carbon atoms. Of those carbon atoms, some are carbon 13, the majority are carbon 12. Do you want to separate that? Like you maybe separate the carbon 12 from the carbon 13? It'd be ridiculous because, I mean, even to count this many atoms, how long would that take you? Well, yeah, multiple lifetimes. So
More than that.
yeah, probably
Half of a trillion, 100 times, like 31,000 years.
31,000 years, okay. So nobody's going to do it then. I mean, even if you had, let's say if you had a computer counting at a gigahertz, how long would it take? Gigahertz is 10 to the 12 per second, cycles per second. Still takes some time. Right? Well, anyway, let's get back to the. So when we're dealing with macroscopic, then we don't care about the individual mass. When we're dealing with macroscopic, we care about the average mass of a carbon atom. When we're dealing with individual particles, we care about the individual mass of the atom. And so let me give you an example of this. Let's say you have a glass of water, you know. How many grams of water did you drink? Well, no, shouldn't you say how many grams, how many different types of water molecules are there? Do you know how many different types of water molecules you drank? This morning. And so the example would be something like this. I'll just write it over here. Example. You know, if you have a glass of water, do you want to know how many grams of H1O16H1 you drank? Okay. What do you think is the next most abundant? Maybe the next most abundant would be H1O16H2. This one weighs 1 U more. Or maybe this one, H2O16H2. Hopefully there's no tritium in the water. We'll just say there's no tritium in this water. So there's no H3. Or H1O17H1. Or H1O17H2. Or H2O17H2. Or H1O18, H1, H1O18, H2, or H2, O18, H2. How many different water molecules did you just drink? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 different water molecules that you just drank. And so if you had, let's say you had a glass of water, 250 grams of water. You had 250 grams of water. How many grams of this did you drink? How many grams of this did you drink? How many grams of this did you drink? You know, do you want to do that? No, you probably don't want to do that. You probably just want to say, well, I had 250 grams of water. That was it. You know. And so what we're concerned with is not, you know, especially when we're dealing with macroscopic, it's not the individual atoms necessarily, and it's not the individual molecules. Although sometimes you deal with this macroscopically, like for example, I bought this. I bought it where they separated out this molecule here, and they separated out this molecule and this molecule. So I only had H2s. I had no H1s. It was very expensive. I had a bottle of that water called deuterated water. Some important properties. Well, the important properties are the magnetic properties. Magnetic properties are part of the physics kind of thing. Had important magnetic properties. But anyway, going back to this. So you know the particle. You know the chemists that are working with individual particles, they care. You know, because they take one water molecule out of that sample. Let's say they have 250 grams of water. They take just one molecule out of that. They want to know which one they took, right? Because it makes a difference. It weighs different amounts. So you got to know which one of these you take. But if we're going to say, okay, I got a gallon of water, then I really don't want to know, you know, how many, whatever. You know, if I have a gallon of water, I just want to know how much water I drank. A gallon of water. This is water. And so what we have is, you know, for the particle person, they represent water like this. For the macroscopic person, we represent water like this. The macroscopic person would represent it as HOH. To the particle person, they want to know, how much does this one weigh about? This one weighs about 18U. This one weighs about 19U. This one weighs 20U. This one is 19U. This one's going to be 20U. This one's going to be 21U, 20U, 21U, and 22U. So the heaviest one is 22U, heaviest water molecule. But to us, do we care? You know what we care? We want the average. Do you know what the average water molecule weighs? And so do you just add these up? 1, 2, 3, 4, 5, 6, 7, 8, 9. Do we add up those 9 masses and divide by 9? Is that how we get the average? That's normally how we get the average. But that's assuming that we have equal amounts of each. We don't have equal amounts of each because by far, which one's the most abundant? The first one. The first one is greater than 99.9% of all water molecules. If 99.9% of all water molecules are this, then the average water molecule weighs about 18U. The average. And that's because of what we call the natural abundances, because this is greater than 99% of all water molecules. And so this is what we call a weighted average. It's weighted based on population. Population of those are the greatest, so therefore they're going to divide. And so the same thing goes with atoms. Of course, you know, we have atom. How much does a carbon-12 weigh? Everybody should know how much a carbon-12 weighs. Well, you have to add something to that. Is that 12U to 2 sig figs? 12.03 sig figs? 12.011? It's not 12.011. You know, it is it's exactly 12. Infinite number of sig figs. Well, how can it be exactly 12? Because it's a definition. It's by definition. It's an arbitrarily picked definition, but it's by definition. And so a carbon-12 weighs exactly 12 U. A carbon-13 weighs about 13 U. And so actually, how much does it weigh? If I wanted to know how much it weighs, actually, I could look it up in the book. But, you know, they didn't put the chart here in PowerPoint. Or did they? They did. And so if I want to know how much it weighs, I'd just go over the a table like this and see. It comes out to 13.003354838 U. This is a lot of sig figs. So what we call it, this is extremely precise measurement of the mass. So we have that. But for a particle, you know, they need to know. They need to know how much that carbon-12 weighs. They need to know how much that carbon-13 weighs. But to a macroscopic person, when there's 602 billion trillion atoms in there, then we don't want to get mixed up in that. We just want how much the average carbon weighs. Now, how much does the average carbon weigh? Now, let me do something for you. Here. So it's based on population. So if we have carbon-12 here and carbon-13 here, and so what we're going to do is we're going to go from this. You know, if we have 0% carbon-12 to 100% carbon-12. Carbon-12. If we have 0% carbon-12, how much percent carbon-13 must we have? 100%. And if we have 100% carbon-13, what's the percentage of carbon-12? 0%. So I'm going to show you another mathematical technique that we use in chemistry. Remember when we have two unknowns, what do we usually need? Two equations. And so we have two unknowns, two equations. This is an alternate method. And so if we have two unknowns, we have two techniques to use to solve this problem. One is system of equations. Two unknowns, we need two equations. The other is the graphical method. And so let me show you the graphical method. And we have two unknowns, how we deal with it. And so if we're at 0% carbon-13, then all the carbon atoms are the same, and they weigh how much? All the carbon atoms weigh 12U. And so that's our first data point there. It's 12U here. Now, if we're at 100% carbon-13, then all the carbon atoms weigh 13U. What if we're at 50-50? Let's say we're at 50% carbon-12, 50% carbon-13. If we're at 50-50, how much does it weigh? What's the average?
12.5.
12.5. And so what we see is we see a linear relationship here. And so what we could do is we can come up with an equation for this. If we wanted. Well, we aren't going to come up with an equation for this because we're just going to do a mental calculation. The mental calculation is this. Okay, let's say it's not 50%. Let's say it's 75% carbon-12, 25% carbon-13. If we're at 75% carbon-12, 20% carbon-13, what's its mass? What's the average? Well, is it more carbon-12 or more carbon-13? It's more carbon-12. And it's right like here, right in this, so it's going to be actually 12.25. And if it's 75% carbon-13, I'm going to check my scales here again, it's going to be more carbon-13-like. It's going to be actually at 12.75. Now let's say it's 90% carbon-12. If it's 90% carbon-12, what's the average going to be? 12.1. What if it's 99.9% carbon-12? 12.01 will be the average, right? Do you know what the average mass of carbon is? The 12.01 is the average mass of carbon, telling us it's 99.9% carbon-12. This only works for two unknowns. Now, if we had 3 isotopes, it's not so easy. You know, if we have 3, like oxygen, it's more tricky because there's 3. But whenever we have 2, it's easy. If we have 2, then we can figure it out. So, for example, the average mass of hydrogen, well, actually, hydrogen is a bit more tricky because look at it, it's 99.988. Actually, it's 99%. There's we'll talk. What did I do? Sorry. If it's 90%, yeah, that's what I did. If it's 90% carbon-12, it's 12.1. If it's 99% carbon-12, it's 12.01. If it's 99.99% carbon-12, then it's 12.001. All right, or 12.01, something like that. I mean, you get the point, I think. But it's, and so we can kind of visualize this. And so let's take a look at chlorine. Chlorine 35 and chlorine 37. There are only 2 isotopes of this, right? Now, 35 weighs about 35. 37 weighs about 37. Now, it's 75% 35, 25% 37. I'm rounding these. Right? So what's the average? Well, let's say it's 50-50. If it were 50-50, what would the average be?
50%.
Well, the average mass, I'd say. 35 and 37. What's the average of 35 and 37?
36.
36. So the average mass would be 36, right? If it's 50-50. But it's 75-25. It's 75% chlorine 35, so it's more chlorine 35. And so what's the average mass if it's close? You know, it would work for carbon because there's only 1 unit. We're going from carbon-12 to carbon-13, which is 1 unit. But this is actually 2 units. We're going from 35 to 37. And so it would be, yeah. So it would be 35.5, right? 35.5 would be the average mass of a chlorine atom. So what is the average mass of a chlorine atom? The average mass of the chlorine atom is, well, I want to show it to you here, but it's 35.45. Pretty good. So you're able to do the calculation in your head. Excuse me. So let's take a look at this. Now, what if we have more than 2? If we have more than 2, then we can't just do a calculation in our head, or we can't do it graphically. We can get more precise with the graphical method here. If we have more than 2, then we use this equation here. And so here we have 3 isotopes. You know, 20, 21, 22. What element is this? It is neon. So let's take a look. Do I have the data for neon? Make sure I have the data for neon. No, I don't. Let's do oxygen. I have the data for oxygen. Oxygen, there are 3, so I can't use this visual method here. I gotta use the equation. And so what's the equation that we use? Well, this is not a straight average. If it's a straight average, we just add them up and divide by 3, you know? But here, what we have to do is we have to bias that average towards the most abundant. And so we do the average atomic mass. The average atomic mass is just called the atomic mass. The isotopic mass is the mass of the individual atoms. Atomic mass is the average of all atoms. Now the average atomic mass, this is going to equal, we do the what we call the abundance, the fractional abundance or the decimal abundance. And so we do fractional abundance of isotope 1 times the mass of the isotope. In other words, the isotopic mass. Plus the fractional abundance of isotope 2 times the isotopic mass of 2. Plus, depends. If we have 5 of them, we got to add up all 5, and this will tell us, you know, what percentage of mass is there. So let's take a look at oxygen. Let's try to figure out the average mass of the oxygen. But now we're going to be precise. We're not going to ballpark it. We're going to go for as many sig figs as we can get. So if we're going for as many sig figs as we can get, so the atomic mass is aka average atomic mass. So the atomic mass is going to equal, all right, what's the fractional abundance of isotope 1? Well, isotope 1 is going to be oxygen 16. And so 99.757 out of 100 are oxygen 16 atoms. And oxygen 16 atoms weigh 15.9949146221 U. And so we have a mix of multiplication and addition. And so I'm going to calculate out the terms first. We have more terms in this sum. Okay, then we go on to isotope 2, which is going to be 0.038 out of 100. How can you have 0.038 atoms? No, you can't. So what we do is we go out of 100,000. If I have 100,000 atoms, then 99,757 of those will be oxygen 16, and 38 will be oxygen 17. Well, how much does oxygen 17 weigh? It weighs 16.999135150 U. And then finally, we go to oxygen 18, the last one. And oxygen 18, 205 out of 100,000 will be oxygen 18. So this will be 0.205 out of 100, or 205 out of 100,000. Just move the decimal over. And those will weigh 17.9991604 U. All right, now we're going to be consistent with the sig figs. And so what I'm going to do is I'm going to multiply this one out here. 99.757 times 15.9949146.221. How many digits does your calculator carry? Yeah, I'm okay so far. Divided by 100. And so the first term I get is 15.956. Now, how many sig figs am I allowed? Well, how many sig figs do I have in 99.757? 5. How many sig figs do I have in 100? Infinite. It's exact. No. think exactly 100, I have approximately 99.757 parts. How many sig figs do I have here? Lots. Right? And so how many am I allowed here? 5. And so this is 5. And so what I'm going to do is I'm just going to carry 1 extra, even 0. Write that as U. All right, plus the second term here. It's a 0.038 times 16.9991315. I don't need the 0, divided by 100. 0.0064. Now, how many sig figs am I allowed here?
6.
Well, it depends. In 0.038, how many sig figs is that? Is that 4 or 2? This is actually 2. These zeros are placeholders. If you wrote this in scientific notation, those zeros would be gone. Or if you wrote this as a part, rather than a part per 100, part per 100,000, it'd be 38 parts per 100,000. Those zeros would be gone. Anyway, continuing on with this, we're allowed how many sig figs here? 2. And so I'll carry 1 extra. 1 extra is going to be 5. And this is going to be U. Plus, okay, now go over here. I got 0.205 times 17.9991604 divided by 100. And how many sig figs am I allowed here? 3. So let's carry 1 extra, which is the 9. Now look how crazy precise the masses are. How come the fractional percentages aren't so crazy precise? Can somebody think of a reason the fractional percentages are not crazy precise because the mass spectrometer is a crazy precise and accurate instrument. And so why can it read the mass to so many sig figs, but it can't read the percentages to so many sig figs?
Is it because the percentage of abundance varies?
Yeah. It's because the percentage of abundance varies depending on where you collect the sample. You know, when I was talking about collecting the sample at the bottom of the ocean versus at the surface, the percentages could vary a little bit because the heavier ones tend to sink more, right? Same thing in for geologists and magmas and that kind of stuff. Heavier things sink. But anyway, taking a look at this here, we can see what part of the mass is. So when we do addition and subtraction, what I do is I rearrange it because I want to align the decimal point. And so whenever I do addition and subtraction, I got to make sure the decimal point aligns. And so this is going to be 0.00645 and 0.03689. Then I look, where is the uncertain digit here? And so when I look at the uncertain digit, this 6 is the uncertain digit here, this 5 is the uncertain digit here, and this 9 is the uncertain digit here. And so how many uncertain digits am I allowed? Just 1. And so if there's uncertainty in this digit here, then that carries over. So it looks like I'm allowed 3 decimal places because I can only have 1 red digit. This one's going to be red digit because I don't know this one so precisely or so accurately. 15.95, oh wait, this is going to be 18, right? 15.998 U. 15.998 U is the average mass of the oxygen atom. Now, when we look at the periodic table, let's see, do we have a periodic table here? I don't want to use this periodic table.
me just show you, since it's hard to see the barricade on the wall. One that goes a little bit farther. Maybe we'll have to look at the one on the wall. Well, let's just look at the one on the wall here.
Can you read that number here? The black one, 15.9994. This one, 15.999. Ours, I didn't add this up correctly. You know what I did?
This is why sometimes I carry extra digits. I have what we call round off.
And so when I did this, I ignored these because I thought, okay, we have this. But if I were to add this correctly, let's see what it adds up to. And so, and this is sometimes why you might want to carry extra digits. I should have carried one extra digit here. If I carried one extra digit here, then it lines up. Okay, so I'm going to have round off error there, but it's all right. We're just going to go with it. And so this is going to be 14, 12, 13, and then this is going to be 18, 19, 15.999 sub 3. Well, they got 15.999 sub 4. And that's because I dropped. I didn't carry this extra digit. This extra digit would have probably made this a 4. Do you see that? So sometimes what we do in our calculations is carry extra digits in the calculator to avoid round off that. But anyway, 15.999U is what we're allowed. We aren't allowed more than that, at least with these natural abundances. And it depends on the data collected from the natural abundances. So the average oxygen is very close to 16, but does it weigh the same amount as an oxygen 16? So let's just take a quick look at that. What did the oxygen 16 weigh? So when we look at the mass of the oxygen 16, look at this. The mass of oxygen 16 is 15.994. The average mass of an oxygen is 15.9994. Look how close they are. They're so close because most of the oxygen in nature is oxygen 16. The little bit of oxygen 17 and a little bit of oxygen 18 bump this up just by 5 or so, less than 5. Just this digit. That was it. All right, so for sulfur, how many isotopes of sulfur are there? There are I didn't do sulfur. There are 1, 2, 3, 4 isotopes of sulfur. And so let's briefly look at how the book does it here. Rather than using fractional abundance, they use a decimal abundance here. So that's 94.93% or 0.9493. And so this is isotope 1. This is isotope 2, isotope 3, isotope 4, and then we combine them. Keeping in mind the decimal, we're only allowed, how many decimal places are we allowed? Only 2, so that we got to drop the 5. If we drop the 5, then this should round to 7. And so let's see, if you go to sulfur, 32.06, so we're off. We're off because of round off error. If they carried extra digits, it wouldn't have been a 5, it would have been a 4. That was the drop digit.
And so these round off errors, I mean, a lot of them are just minor, but that's it. And so what we see here is this. You know, we have the atomic number, which is the number of protons, which dictates what element. You know, the element's dictated by the number of protons. And then we have the atomic mass, aka what? The atomic mass is also known as the average atomic mass. If you were a particle chemist or particle physicist, would you want the average or would you want the individual? You wouldn't want the individual, so this isn't as useful. I can tell, you know, probably what the most abundant isotope of sodium is. You know, what do you think the most abundant isotope of sodium is? Sodium. Not the compound, but the most abundant isotope of sodium. I'm asking you this. What is the most abundant isotope of sodium? 23. The most abundant isotope of sodium 23 has got to be sodium 23 because the average is 23, and so it's probably close to the average. It may not be, you know, right on 23, you know, but it's got to be close to 23 for sodium. Let me see the data. I have the data. All right. Let's take a break now, and then we'll continue. We're almost done with chapter 5. Finish that up after the break. Yeah.